Now we know why somebody might want to stop and find the area under a velocity curve. They can find area under velocity curve that gives distance traveled. So, all the examples we've done so far, we had a velocity curve for which, when we tried to draw the area underneath the velocity curve, we had a shape, and we could figure out the area of that shape using geometry that we already knew. What if I want to find the area under a velocity curve and I don't have a regular geometry shape to have a formula for to find that area? So let's take a look at this example. What if I had a velocity curve v is 1/8 t squared plus 1? It's not that exciting a curve, it's just parabolic, it's degree 2. But we don't probably know offhand a formula for finding the area under a parabolic curve. So we're going to learn later this semester, but right now our best answer is to find an approximation. The same way before we really knew how to find a derivative to give the slope of a tangent line, we could approximate the derivative by finding the slope of a secant line. So here, if I don't know the area under this curve, I can approximate the area under the curve by splitting up that area under the velocity curve into a bunch of rectangles and adding together the areas of the rectangles. Why rectangles? Because to find the area of a rectangle is super easy. It's just length times width. So there are two important decisions you have to make when you want to approximate area under a curve using rectangles. Decision number one, how many rectangles will you use? The more rectangles you use, the better an approximation you'll have, but the more calculations you'll have to do, the more exhausting it might be, the more places you can make an error. The other question you would have to answer is, how are you going to choose the height of the rectangle? Once you decide how many rectangles to use, you just chop up the whole distance you're trying to cover into that many sections, and it's easy to figure out the width. But how do you figure out the height of the rectangle? So you could just make a decision. One option is to choose the heights of the rectangles so that the top corner, the top left corner of the rectangle touches the curve. So notice here, my first rectangle, its top left corner touches the curve at the same place. It's as if I put 0 in, plug 0 in for t. Since 0 is the left-hand side of this rectangle, which covers from 0 to 1. Pick the left-hand side, just to pick something, and use the height of the rectangle as the value of the curve, the value of the function, when time equals 0. The second rectangle covers times from 1 to 2. The left-hand part of that interval is time 1, so I'm going to choose the height of my rectangle as if I had let t equal 1 and plugged it into the velocity curve. So I can add up the four areas of these four rectangles. Each one of these rectangles happens to have a width of 1, and there are 4 different heights for the 4 different rectangles. You can see them here. And I can multiply length times width for each of the 4 rectangles, add up the 4 rectangles, and I have an approximation for the area under the curve. In fact, you can see that approximation here. Now, I happen to be able to tell here. I won't always be able to tell. But here I can tell. Look at this. I have, every time I made a rectangle, that rectangle, there was a little space left over that I didn't quite cover with my rectangles. So it turns out that each one of these rectangles is a little bit too small, so I know my final answer is going to be an underestimate. Remember that decision to have my rectangles touch at the top left corner was just sort of a decision, an arbitrary decision. I could have had my rectangles touch at the top right-hand corner. So think of that first rectangle, it covers the t values from 0 to 1. The right-hand end of that interval is 1. So if I plug 1 into my velocity function, I'm going to get 1 and 1/8 as the height, which is how I chose this height for that rectangle. And I can do the same thing. So use the right-hand corner of the interval as the t value to plug in to get the height of the rectangle. And you can see here, each one of these rectangles overestimates the actual area a little bit. Here, I would have an overestimate. Notice this is called the right-hand rectangular approximation method because I've used the t value from the right-hand end of the interval to compute the height of the rectangle. So RAM for short, right-hand rectangular approximation method. When I had the left-hand corners touch, that's the left-hand rectangular approximation method, LRAM. And there's one more you need to know about. I could have had my rectangles touch at the middle of the intervals. This is called the midpoint rectangular approximation method, MRAM. Notice here that first rectangle covers from 0 to 1. Let's get a pen here. From 0 to 1, the midpoint of that interval is 0.5. So if I used 0.5 as the t-value, I would get a velocity of 1.03125. And that's the height of that rectangle chosen here. Oops. So trickier to compute, it definitely would be harder to do by hand, but your calculator or a computer would have no problem with this. So those are the three different rectangular approximation methods. We're going to practice them next.